Welcome back. We're going to continue with Factorial ANOVA. So again, going kind of in reverse order to the order in your textbook, but I think it'll help with the flow and kind of conceptual level of this. So just to recap a little bit, we've covered our one-way ANOVA, so one independent variable. We said that could be either between groups, like our independent samples t-test, or we said it could be within groups, or repeated measures, which again mapped onto our paired samples t-test. So next we're going to look at a factorial ANOVA, or what we call a two-way ANOVA. And in this example that I'll walk you through, I'm going to use two-way between groups ANOVA. So I'll have two independent variables, both of which are between groups. But again, just to reiterate, you could mix a between and within, you could have two within, you could have any number of variables you choose. But again, I think the two-way between helps keep it simple for now. A question that comes up a lot, especially when you're reading journal articles, is how to name an ANOVA. And you've probably seen this before in either results section of a journal or maybe in the methods section, the proposed analysis section. But typically when we describe ANOVA, we can kind of map this out using this table here. So first, the number of independent variables we have. Again, we talked about one-way, two-way, three-way. Obviously there are more than just three that we can have, but again, for the sake of keeping it simple. The second kind of point of information you'd want to pick out is it between groups, within groups, or a mixed design? And then we always follow it at the end with ANOVA. So you can imagine a one-way between groups, a two-way between groups, a one-way within, a two-way mixed, and so on and so forth. So you can kind of see the different combinations. So hopefully that helps a little bit when you're reading a journal article and they're describing an ANOVA to really pick out how many variables are they interested in, and are the participants all in one group, or are they the same group over a period of time, or a combination of the two. On this slide, we have a little diagram. So we talked, when we first introduced ANOVA, this idea of variance, and that we're analyzing or doing our analysis of variance by comparing a ratio of our within groups variance to our between groups variance. So we said that that's what that F ratio is examining. So we're assessing the between and within variance, and that's really, and that those two add up to our total variance. So total variance is a function of the between group variance and within group. So our factorial ANOVA actually takes this a stage further, because then we can take the between group variance and further partition it out based on different variables or factors. So we'll have variance associated with factor A, or one independent variable. We'll have variance associated with our second independent variable, or factor B, and then we'll have what's called an interaction effect, or interaction variance. So a lot of times our variables that we're interested in measuring, they don't exist in a vacuum. There's overlap between them. If you think of something like ACT score and grade point average, they're measuring two different things, but those two concepts are likely related. There's some overlap in them because they're both meant to be kind of proxy measures of your intelligence or your academic performance. So we would have variance associated with ACT score, variance associated with GPA, and then we'd have a measure of kind of the variance or the overlap between those two factors. So really, when we're running our factorial ANOVA, our source table becomes a little bit more complex because we're going to have a measurement of all these different variances. So I realized talking about these different types of variance, it's a little kind of pie in the sky theoretical, so it might help to look at an example. So your textbook describes an example of looking at the television viewing habits, kind of asking, do boys and girls watch different amounts of TV? And also, does it depend on what part of the country a child lives in? So if we were to kind of set up this research question as a factorial ANOVA, we could talk about what's called two different main effects. So I could say for a main effect of gender, not taking into account where someone lives, just looking at gender, do boys watch more television than girls? And again, I would measure amount of television watched. I could measure it in hours. I could measure it with a scale. But again, something I can take the mean of. And I want to know, does this differ for boys or girls? So that is one main effect. The second main effect I might be interested in is a main effect of region or where someone lives. So the book chooses north, south, east, and west. So 4 different regions of the United States. So again, we could compare hours of television watched. Again, not differentiating between boys and girls, just all children as a whole, television watching habits of all children for those 4 different regions in the country. And that would be a second main effect. So you can see here that main effects are differences between the group means on the dependent variable for any independent variable in the ANOVA model. You could also imagine, though, that maybe we think that the television watching habits for a boy or girl depends on where they live. It's influenced by the second factor. So again, the interaction effect is present when the differences between the group means on the DV for one variable varies or depends according to a second independent variable. So it could be that maybe boys watch more television overall, but maybe girls in the South watch more television than boys in the South. So we're able to really drill down and look at what we call those interaction or moderator effects, looking at television watching habits based on both gender and where a child lives in the country. So you can see that it's able to ask a much more complicated research question rather than just who watches more television, boys or girls, north, south, east, or west. So we're really able to kind of cross those 2 effects together. So for the purpose of this example in the textbook, we actually have 3 different hypotheses. So we have first a hypothesis related to that main effect of gender. So who watches more television, boys or girls? The second main effect is a main effect of region. So do children in different parts of the US watch different amounts of television? And then the third, the interaction effect, combines those 2 main effects. So do the television habits of boys and girls depend on what part of the country they live in? So we're actually testing kind of 3 different hypotheses here in our factorial ANOVA, rather than kind of running all these different statistical tests separately. So we're able to do it all at once and ask kind of more complicated research questions with the factorial ANOVA. When we're setting up our factorial ANOVA, we want to be sure that we really define what our variables are. So again, we have our first independent variable of gender. It has 2 levels, boys versus girls. Our second independent variable is region, and again we have 4 levels, north, south, east, and west. And our DV is always something we take the average of, so in this case it's hours of television watched. So in terms of naming this ANOVA, you could name it based on that ANOVA table a couple slides back. It would be a 2-way ANOVA because we have 2 independent variables, and both of our independent variables are between groups. So you're either only in the boy group or girl group, you either only live in the north, the south, the east, or the west. You can't be in multiple groups. So a 2-way between groups ANOVA is one way we could name this. There is also another way that you might see in a journal article, the second option here. And in this case, where the numbers and how this is broken down is that the number of numbers represents the number of independent variables. So I have the number 2 and the number 4. So I have kind of 2 numerals here. And then the value of the number represents how many levels. So my first independent variable of gender has 2 levels. My second independent variable of region has 4. So that gives me a 2x4 between groups ANOVA. So again, both of these are correct ways of describing it. It might differ depend on the type of journal or what area you're reading literature in. So both of these are accurate ways to describe this particular ANOVA. I'll jump over to SPSS in just a minute here and show how we can walk through and run a factorial ANOVA. Here's kind of the shortcut of commands. But again, just to reiterate, whether we're running a one-way, a between groups, a within groups, or a factorial ANOVA, the underlying process and calculations are the same. So for each variation of ANOVA, we're calculating different sums of squares, different sources of variance. So whether it's total, within, or between, we're inputting that data into an ANOVA source table. And ultimately, we're taking the data in that source table to create that F ratio. So figuring out if we have greater variance between or within our groups and whether or not that's considered statistically significant. So again, how discrepant do the number of hours of television watched between boys and girls, how discrepant do those values have to be in order for us to conclude that there's a statistically significant difference and one group is watching way more television than the other? So again, the underlying calculations are the same. It's just quite tedious to do those by hand. So we'll go and jump over to SPSS and look at how we can run our factorial ANOVA example. I went ahead and opened SPSS and entered some made-up data to try to mimic the example in your textbook. You can see here I have 3 columns of data. I have gender, region, and number of hours spent watching television. So I'm going to go ahead and go into the variable view and label my data in SPSS. So again, the first variable was gender, second region, and this third one, we'll call it TV hours. Again, we can't have spaces or special characters in our variable names, so it's okay to kind of give them short, condensed names as long as they're meaningful to you. All of these are numeric, and under measure, I'm going to go ahead and tell SPSS that gender and region are both nominal, so they're both categorical variables, and number of TV hours is a scale variable. Now you can tell if you go back to the data view that I coded both gender and region with numerals, so it might be nice to tell SPSS and to remind myself how I coded those. So if I click on gender and variable view under values, this box with the 3 little dots, I'm going to go ahead and say that I labeled 0 as boys, 1 as girls. I'm just going to add those and then hit OK. I will do the same thing for region. So 1 was north, 2 represents the south, 3 represents east coast, and 4 represents the west coast. So again, I'm just adding those and then hitting OK. So going back to the data view, you can see that the way that we enter our variables, especially the between groups factors, is really important. So this first participant, you can tell, was a boy living in the north region, and he watched about 26 hours of television. And you can kind of go down and see boys versus girls and the different regions and how they vary from one another. So being able to kind of keep those categories straight is really important when you're initially setting up and coding your data. To actually run our factorial ANOVA, we're going to again use the Analyze menu. Again, we'll be under General Linear Model. If you recall, last time we used the repeated measures, and this time we're going to use this very top one called univariate. So you can see here we have our dialog box. The first thing we want to do is define our dependent variable. So again, it's always something we take the average of or as a scale variable. So I'll transport number of TV hours over there. And then my independent variables, I'm just going to transport into this box labeled fixed factors. Your book goes into some other detail, how you can add covariates or additional variables to create something called an analysis of covariance or an ANOVA. But again, we're going to keep it simple with this first example here. Under the Options button, I'm going to go ahead and click on Descriptive Statistics and hit Continue. If you recall last time, I said that we didn't need to click on the post hoc button for repeated measures, that was only relevant when we had a between subjects factor. So for this particular example, we have 2 between subjects factors. We have gender and region. So I will click on the post hoc button, and I'd like to run post hoc tests for both of these. And again, below here, we have a number of different post hoc tests. I'm going to click on Tukey because that's what we've used before, and then hit OK or Continue. The last thing that we might do is we could create a graph or a plot of our data, especially when we're talking about interaction or moderator effects. Sometimes it's easier to interpret when we have a visual picture of it. So I'll click the button labeled plots, and I'm going to go ahead and enter region on the horizontal axis, and then I'll make separate lines for boys and girls. And I'll just go ahead and add that. There's a couple different ways you could do that. You could flip those two around. This is just one example of a plot that we might run. So after I hit add, I'll hit continue, and that's all I will do in those kind of optional menus on the side there. I'll just go ahead and hit OK to run this. So here we have our output window, and you can see at the very top, SPSS is giving us a warning message, and it's telling us that they are not able to perform a post hoc test for gender because there are fewer than 3 groups. So that makes sense. We don't really need to do a pairwise comparison. We can simply look at the means to determine which is higher, boys or girls. The second box here, our between subjects factor. This gives us some descriptive information. It tells us that we had 16 boys in our sample, 16 girls, and we had 8 children from each region, north, south, east, and west. If we jump down a little bit further, we have this box of our descriptive statistics. And this one, it's a little big, but it contains a lot of useful information. So you can see here under gender, if we look at the total number of TV hours watched for boys, we're almost at about 22 hours versus total for girls is about 14.8, almost 15. So it appears that so far boys are watching more television than girls. And you can see here under total, regardless of gender, the children are watching on average about 18 hours of television. Similarly, we can kind of compare across region. So regardless of gender, it looks like the most number of hours of television watched seems to be in the north. It looks like the lowest is in the south, and east and west are pretty close. We have 17.5 versus 17.37. So that gives us kind of an idea of the overall regional trends. And then up here is where we get into kind of the nitty-gritty comparisons. So for example, we could have boys in the north are watching about 25 hours. Girls in the north are about 19, almost 20 hours. Boys in the south are about 22 and a half versus girls in the south are only at 10. So really what our ANOVA is going to do is give us an F-test or a hypothesis test for this boys versus girls comparison. This about 22 hours versus about 15 hours. It'll also give us a test for these different regions regardless of gender. And then more importantly, it's going to give us that interaction effect, which is testing kind of these nitty-gritties up here in that column. So it's able to do all of that at once. When we scroll down a little bit more, we have this table labeled Test of Between Subjects Effects, and this is really our ANOVA source table. It's just been expanded a little bit to account for the fact that we have multiple independent variables. So you can see this very first line here that says corrected model. This is kind of our overall, or sometimes it's called an omnibus test. And this test value, the F ratio of 6.35, you can see is considered statistically significant. So again, that's telling us that we have some kind of significant effect happening somewhere in this model. So that's kind of useful as an overarching idea, but really what we're interested in are the lines for gender, region, and the gender by region interaction. So you can see here for gender, if we go across that row, again, we have our sums of squares, our degree of freedom, our mean square, our F ratio, and a corresponding significance value. So we can see here we have a significant F test of about 26.99. It's considered statistically significant. So on average, again, if we go back up to our descriptive statistics, boys are watching significantly more television compared to girls in this sample. Similarly, if I look at the main effective region, I have my sums of squares. It's 3 degrees of freedom because we had 4 regions we were testing. We have mean square, and we again have an F ratio. This F ratio is smaller. We're at 4.074, but you can see this F ratio is still considered statistically significant because that sig column is less than 0.05. So this is telling us that there is a significant effect for region. What part of the country you live in may help determine how much television you watch. In this case, though, we can't simply go back up and look at the means. That's where we're going to need those pairwise comparisons. And last, if we look at the gender by region interaction, again, we just come across this row. Here we have an F-test of 1.745. And you can see here that the significance level is not quite reaching that 0.05 cutoff that we'd like to see. So it looks like there's not a significant interaction going on between gender and region. But we'll dig in a little bit deeper as to what that looks like. We'll keep scrolling down here on our output, and here we have our post hoc test for region. So again, these are our paired comparisons. So looking at the difference between North and South, and again, this is regardless of gender. This includes all children in the sample. So between North and South, we have a difference of about 6 hours in television. And again, if you go back up to that descriptives table, you saw that indeed, children in the North were watching quite a bit more television than those in the South. And because it has the little asterisk and the significance column is less than 0.05, we'd conclude that children in the North are watching far more television than those in the South. It's considered a significant amount. If we look at North versus East, we see here a difference of almost 5 hours. So although it doesn't seem that different from 6 hours, the significance column is not less than 0.05. We're at 0.076, which some people would consider to be marginally significant. So it's getting close to that 0.05, but we have to draw a line in the sand somewhere for that cutoff, and it's not quite reaching it. So we would conclude that children in the North versus the East are watching, on average, about the same amount of television. It's not that different. Similarly, looking at North versus West, again, we're at about a difference of 5 hours, and you can see similar to the one above, it's not quite reaching that 0.05 of significance. So really, if we go down the rest of the column here, the only significant one that we're seeing is the difference between North and South, or here the difference between South and North. It's the exact same thing, it's just a mirror reflection. The significance column is the same. So really we're seeing a significant difference between the North and the South, but in terms of comparing the other regions to each other, it's not quite discrepant enough for us to conclude that it's statistically different from each other. We can continue to scroll down. This box labeled homogeneous subsets, we can go ahead and ignore that. What we're really interested in, though, is the plot that we asked for. So you can see here we have estimated marginal means of number of television hours watched. Along our x-axis on the bottom, we have by region, and we have a blue line for boys and a green line for girls. So you can see across the board that boys are quite a bit higher. You can see here the line for the girls fluctuates quite a bit more. And you can also compare the data points based on region. So again, comparing kind of the North versus South, you can see here that the girls in the South were quite low compared to boys in the South. So that would be an example of that interaction effect. So although we have quite a large spread here in the number of TV hours watched, our tables up above are telling us that although it's a large difference, it's not considered a statistically significant difference. And part of that could be that we only had 8 children in each region, so that's a fairly small sample size. So you could imagine that difference might change a little bit depending on if we had more participants in the study here. So again, that gives you kind of an overview of the Factorial ANOVA, how we run it, how we input the data, how we can interpret the different comparisons and post hocs, and how we can also generate a plot to help us visualize this. Going back to our slides just for a minute here, again, these were kind of the shortcut commands. I realize there's kind of multiple steps involved in these more complicated ANOVAs. Again, be sure to visit the handout that's posted on the course site. as well as in the future, if you ever need to run one of these, the textbook's a really good resource, or even just Googling. There's a lot of great tutorials out there on YouTube and various other sites. So once you've run a couple of these and you kind of have a template to go off of, it definitely gets easier in the future remembering where to click and what button to go into. So that will do it for our different types of ANOVA. Again, we've covered that one-way ANOVA, the repeated measures, or within groups ANOVA, and the factorial ANOVA that combines the two of them together.